Okay, and we should be on my, yeah, we're on my mic, your mic's off, right?
Yes.
Okay. Hi, this is Exploring Light. We just had some technical difficulties for the last half hour, but we're back online, and we're going to continue with your questions, and Paul Doherty has a bunch of things to present to you. So we're going to hop right into it. Paul?
All right, so it's about light as a wave and a particle, and I wanted to start with one of the really beautiful art and science illustrations about light as a wave. So I'm going to head back over to the other table. We have a snack in which we have you take a film can or an old made film, put it into dishwashing water, 10 parts of water to 1 part dishwashing liquid. Put on a white screen and the transparent dishwashing liquid. As bands of color in it. Where do the bands of color come from? It's on. Oh. So where do the bands of color come from in that film can? Well, we have a model here of waves. I have the red wavelengths. And these cards are about 7 inches or 15 centimeters in length to model the red wavelength. And I have 2 sets of cards here. One to model the fraction of the light that reflects off the front surface of the soap film, and one to model the reflection of the back surface of the soap. The blue table represents the soap film. The soap film is made of 2 layers in blue of molecules that make up, and in between them is a mixture of water and soap molecules. So the light comes in, and most of the light, 96% of it actually, goes straight through the soap film. And then we stop at some point. There. Usually I stop on the first surface. And then the first bit of light reflects back off the surface. Pull through, and then the light, because I only want to look at the reflected light. It's reflected right at that edge. And the thing is, when light is reflected off the surface, it's over. Then, what happens at the back surface, I fold it right at the back surface, and that one does not flip over. So I fold it at the back, coming out, through, line them up, find out that when this light is reflecting off of a soap film, that is 1/4 of a wavelength of red light thick. The peaks and the valleys line up on the 2 waves. And that gives us a strong red reflection. And having the students actually as shown in the video, it's a really good way for them to understand the wave nature of light. Use it to understand the wave nature of light. So in addition to this, since light is a wave, it can go through slits and diffract, as we saw in the week. And we use that this week to make something called a compact disc spectroscope. And you saw on the video how to make it. And what you can do is look through the opening at a reflection off the compact disc of light coming through a slit, and it will break up that light into a spectrum of light. It's a really nice tool. Now, one of the things you can look at that's very exciting is sunlight, but don't look at the sun. Look at a piece of white paper in the sun, or look at a white cloud in the sun. And when you do that with a really nicely built compact disc spectroscope, some of you have noted that you see the continuous spectrum you expected, but in that continuous spectrum, there was actually black lines. I'm going to try to share with you on the screen an image of those black lines. So I'm going to, let's see, in order to share, I can turn on my camera. lines of light. In order to get a beautiful line of light, you need a low-density gas. Solids and liquids and dense gases do not give out lines of light. They give out a continuous spectrum. But above the surface of the sun that gives off the light, there are other layers in the sun. And when the light comes into those layers, the same wavelengths that would be emitted if the gas were hot are absorbed by the cold gas. And so the bright sodium line that you see in a candle flame with salt in it becomes a dark line because in the upper solar atmosphere, the light coming from the sun to you is absorbed by the sodium atoms that are in the solar atmosphere and then re-emitted in a random direction. So the light that was headed to you heads off to the side. And that's the answers to the question of why are the Fraunhofer lines dark, is it has to do with geometry. And these were discovered in the 1800s by a German surveyor by the name of Fraunhofer. And if you discover something in science, sometimes it's named after you. Any comments from the team on Fraunhofer lines? Have you managed to make a spectroscope that showed these?
I haven't seen that. Actually, you know, I've done it with toilet bowl cleaner.
Oh, yeah.
It blocks it out, yeah.
So there's a kind of blue toilet bowl cleaner in the United States that if you look at a continuum source of light, an incandescent light, through a container of this toilet bowl cleaner, it's a blue toilet bowl cleaner. It has a strong absorption in the red. And it's called holmium chloride. Holmium is an element in the periodic table, and holmium chloride absorbs red light in a nice band, which allows you to see the blue color. So it's a nice hands-on model for how to do this.
And you can clean your bathroom bowl too.
And it makes your bathroom bowl smell good at the same time. Okay. Clean up a moment, the demonstration table. And now I'll bring over something from a past week we also had a question about. It turns out one thing I had you do was to look at static electricity. And people were wondering, what does this have to do with light? Why are they having me look at static electricity? So what I did was I took 2 pieces of tape. Am I on yet? So I took two pieces of tape. I used Scotch Magic tape, almost any tape works. And I put the sticky side of one tape on the smooth side of the other. And then I pull them apart quickly. And you find that when I do that, they attract each other strongly. I can put them on some bent soda straws here as holders, so they stand out. And then I can charge up. I have some PVC and wool. And when I do that, I can push or pull on those tapes at a distance. So when I wave this electrically charged PVC, it's negatively charged back and forth, the positively charged tape alternately comes towards it and away. We look at it from here. Now, what's happening is that a force is traveling over the distance between the PVC pipe and the tape. And Mr. Faraday decided to model that by saying that the force was created by an electric field, that the charge on the pipe created an electric field in space that reached out around it, and that electric field then exerted the force on the tape. But what that means is, as the tape goes back and forth, that as I wave this pipe back and forth, there is a wave in the electric field going out between the pipe and the tape. After Faraday, James Clerk Maxwell studied the waves in the electric field and discovered that when he combined the electric waves and magnetic waves, they traveled at a certain speed. And that speed was the speed of light. So he guessed that light was made of electric and magnetic fields, that the waves of light were waves in the electric field. And what this experiment shows is that the electric field can cross empty space. You say, well, there's air in this room, and maybe air is carrying the electric field. But even if we did this in the vacuum of space, and it has been done, the electric force will cross the vacuum. Students often can understand this because they see it in class, but they have trouble figuring out how light can cross the vacuum from the sun to the earth. So what we say is, electric forces can cross an open space. Light is a wave in the electric force, and that wave can also cross the vacuum of space. It's a really nice way to lead students to understand that light is an electric wave. I don't know if there are any questions out there coming in or not, if we have any viewers, but I'm sure we'll have people watching it later. So that leads us to the fact that the speed of light is 186,000 miles a second, or 300 million meters a second. And that leads to something that Eric Muller is going to demonstrate, and that is the speed of light in a different set of units. So Eric?
Yeah. So it turns out that light travels at 3 times 10 to the 8 meters per second, which is pretty fast. But if you want to get a usable unit that you can hold in your hand, if you, instead of saying it's traveling that far in a second, if you say, how far is it traveling in a nanosecond, which is a billionth of a second, it turns out if you do the math, it goes about a foot. Or if this was optical cabling, it would be going through this in about a nanosecond. And instead of calling it a foot, hey, you guys over there, instead of calling it a foot, is it called a foot? Like this foot right here?
It's called a foot, but spelled differently.
It's spelled differently. It's P-H-O-O-T. So if you're going to send it through optical cabling, this would be about how far it would go in a nanosecond. But actually, I like to use this. This is just a pipe. This pipe is about 30 centimeters long, or about a foot. And so the light coming from the sun, if I look through here, in 1 nanosecond, the light has traveled from this end of the pipe to this end of the pipe. That's a foot. 1 nanometers distance of light.
And foot, P-H-O-O-T, is an anagram for photo, which is a nice way to remember it.
Yeah, just so you know, if you Google it, it'll always say, oh, you don't mean foot, do you? With PH, it's photo. It'll actually keep switching it on you. Yeah.
So like a light year. Light moves in a year. So that's a light nanosecond. That's right. That is a light nanosecond. Okay, so, but how far, you know, is talking about light? If you were able to see a wavelength of light, how big would that be?
So light now is not just the electromagnetic wave from the 1800s. So it's not the electromagnetic wave from the 1800s. It's actually, in 1905, Einstein discovered that light traveled in quanta of energy. So light traveled in quanta of energy, which in 1926, William Gilbert named photons. And these photons of energy had a certain length to them. The average photon emitted by light length of an average photon here. I'll hold on to the first two. So we'll come through. So this will actually represents. Oops! The photon broke. There we go. And it's even hard to see. It's just so large. It's hard to see this entire photon.
I zoomed into the photon. Yeah.
Yep, as far as it goes. But this is the 3 meter length. And the thing is, it's like a really thin piece of spaghetti. It's actually only half a wavelength of light from the middle to the edge. So a photon is a long thing. And I'll be describing to you in a minute what's really going on here. Now, this probability of this being a photon actually does spread out to infinity above and below and front to back and end to end. But the major probability of detecting it is within 3 meters. And that's a model you don't see very often. By the way, at the speed of light, it takes about 10 nanoseconds. So in 10 nanoseconds, and 10 nanoseconds is how long it takes on the average for an electron to go from 1 p higher level energy in an atom to the s level. So a photon comes out of an atom over the time that it takes the atom to transition from a high energy state to a low energy state. I'll model that for you in a minute as well. And in that time, the light coming out can travel 3 meters. So that's why the photons are about this length. So let me retire my photon, and now it sticks together. Okay, so I'm going to show you a couple of images on screen. Let me close off this one, and I'll bring up this one. So, can I share this one, Eric? Just a minute. I'll get back. Oh,
yeah.
It'll be connected to RAT.
You need to get your.
Oh, yeah, it's up here somewhere.
Your Google.
That's here.
And go to right there.
There we go. Yeah. So here's some information about a photon. What I've drawn here on this image is what you see is a wave, and in this 3 meter long wave of a photon, there might be almost 10 million waves. So you think of the wavelength of light, and it's quite short, it's 500 nanometers. But the total photon is 3 meters long. So there are like 10 million oscillations within one photon. But those oscillations in the modern quantum mechanical view are not electromagnetic. And you can see that these waves have an envelope. They're very small at the beginning of the wave, and they're maximum in the middle, and very small at the other end in this diagram. Okay, so let's go on to the next image. I'll open another one. Oops. I'm switching, just taking a minute. So in the next image, is this going to show on the screen, or do I have to go back and reshare it?
Yeah, go back on and just say, okay, back to Google.
There. And we'll share this one. So here we are finding that the average wave packet is a little bit longer than a human arm span. And in one wave packet of light, there is actually 6 million wavelengths. The number of wavelengths depends on the wavelength of the light, of course. So just another way to show that. And open another one. Just to give you an idea of the size, it turns out that if we look close up at this, you'll find that little dot is representing an atom. And in one wavelength, there are 100 dots of the size that I showed you in that illustration. in one wavelength of light, there are 5,000 atoms. So one wavelength of light is 5,000 atoms across for middle of the visible spectrum. There are 10 million wavelengths in a photon. And the next slide is the most important thing about quantized light.
Hey, before we move on, what does that mean there are 10 million waves in an atom?
In a photon.
Oh, in a photon.
In a photon, there are 10 million wavelengths in the 3-meter length. That the frequency of light is like 10 to the 15th cycles a second. There's not, there's hardly a easy name for 10 to the 15th. Petacycle or petahertz or something, but pentahertz. Yeah. So, but now let's see what that actually means, and this is the essence of the quantum mechanics of photons coming up. We'll open the last of my images to share, and we'll share it right here. Hey, how come it's, here we go, let's back up. And here we have what's really going on, okay? So the wave packet is shown in the top here. That is the photon of light. Low probability at the front, building to a high probability in the middle, and then decaying. And the dot in the middle here is an atom. And then the wave has moved halfway past the atom, and finally the wave is departing the atom entirely. At some point, as the photon moves past an atom, the entire photon vanishes, and its energy goes into the atom. This atom that is 1/5,000th of a wavelength long, which is 1/10,000,000th of a photon long. It's called, in quantum mechanics, the collapse of the wave function. This probability that it is the photon passes the atom, and at some point, at the beginning, at the middle, or at the end, it completely goes away, and its energy in its entirety goes into the atom. And that's what we mean when we say that a photon is a particle, that it is created, all of its energy is created, or none of its energy is created. All of its energy vanishes, or none of its energy vanishes. Your students, when they hear particle, they think ball or rock or grain of sand. It's not that kind of particle. It's a quantum mechanical quanta. And so getting them to think of it in this strange way as an all or nothing. So one way that scientists think of this quantum mechanical model is by saying that light travels as a wave, this 3-meter long wave traveling, but that it's created or destroyed as a particle. The whole quanta comes into existence, the whole quanta vanishes. And if you keep that model in mind, that the creation or destruction of a particle is viewed as a particle, as the photon is born or dies, and as it travels, you consider it as a wave, that will give you the simplest modern model of a photon. So questions from the crew or comments to add in?
Nutty stuff.
It's nutty stuff. It's quantum mechanics is not our everyday life.
Yeah. Hey, are there any other good resources to figure out the quantum model?
There's a great book to learn about this quantum model, and I think Zeke mentioned it to me the other day.
I'm a big fan.
Come on over and sit down.
And
yeah. That's good.
So I'm a big fan. Richard Feynman has a book called QED, which I'm a big fan of, and it explains, it gives a model of how light works in 3 longish chapters. It but he explains it very, very clearly of this idea that light might be particle, might be this little, we'll use particle loosely here, but it's a small thing that has a certain probability function associated with it. And that moves through space, and he explains this out in a very complicated way, but giving lots of examples, lots of details to go along with it, and then you can, at the end of the chapter, he says, now, if we imagine these things to exist, we can imagine that it has certain properties, and you can show that those properties have the same properties that we experience when we look at light, and we look at the interaction of things like as simple as lenses and as complicated as diffraction gratings. And it's weird because he says at the beginning, like, I'm going to assign these properties to these little particles, whatever that is, and I'm now, like, it's hard to imagine that these things might actually be real, but yet they still have the same properties as the as light actually does. And it gives an interesting background to the idea of what is real, what does it mean to have a scientific theory. If the theory explains what actually happens, does that make it a correct theory? Does that make it real? Like, there's a lot of really deep interpretation about, like, what makes a good model and what it means to have a good model in QED. It's a fascinating read. My high school students usually could understand it with pretty good facility with the ideas in it, and it made them really interested in the nature of modern science. It's a fantastic book. QED by Richard Feynman.
I recommend it highly. I really enjoyed that book. In fact, this model that I gave you of light as a wave and probability comes from that book by Feynman. Mm-hmm. Might as well steal from the best.
Absolutely.
Well, the idea of quantum mechanics applies also to the atoms themselves. And so inside the atom, the energies that an electron can have are quantized. And that leads to some interesting properties. And in fact, I'm going to show you a couple of interesting properties using things called light-emitting diodes and solar cells. And both of these can be understood with a very simple model of energy levels inside of an atom or a man-made compound. So I'm going to walk back over here, grab some things. Where would be the best place for me to be to demonstrate this?
You want to get on that thing? Actually.
Clay ball is an electron. And I have this slope here. The electron could have any energy along that slope. But that's not what happens in the real world. It turns out that inside of an atom, an electron can have one particular energy or another. And it can't ever go halfway. It's got to go all the way or not at all. And this lowest energy here I'm going to call the ground state energy. And here we have an excited energy. What I'm doing here is raising it up against gravity. I'm using a gravitational energy to represent the electrical energy. And what happens in a light-emitting diode is we have an electron, and we give it some electrical energy called voltage, and that voltage raises it up to a higher energy, and then it can fall back. But it's been raised up by electrical energy, but when it falls back, it gives out light energy. And in particular, we have a handout in which we describe the energy of light as a function of voltage. So I have a voltage source here that I can dial in the voltage, and I have light-emitting diodes. And as I turn up the voltage, you'll see that first a red light comes on. Is that showing? First a red light comes on. I'm continuing to turn up the voltage, and then a yellow light comes on, and then finally a green light, and then a blue light. So as I turn up the voltage, I get red, and then yellow, and then green, and then blue. And what this is showing you is that the light-emitting diode is like a man-made atom. It has two energy levels. The lower energy level is called the valence band, and the upper energy level is called the conduction band, and there's an energy gap between them. And these man-made atoms can be made to have a low energy that when I excite, which is the red one, I excite the electron up and it falls off, it gives off red light, or it can be made with a higher energy, and I can excite it with a higher voltage to higher energy, and when it falls off, it gives off blue light. And we can make many different compounds. For example, aluminum, indium, gallium phosphide. It's a man-made combination of those elements, which makes a blue light-emitting diode. And by using different compounds, we can make different man-made energy levels and have different colors of light come out. So to understand what a light-emitting diode does, you have to understand energy levels and the fact that when an electron goes from one energy level to the other, almost all the time, it gives out one photon, one quanta of light as it changes energy levels. That is a really great fundamental idea. But it also works in reverse. So what I have here, and another activity, another snack that we've written up, and that is a solar cell. And on the back of the solar cell there are two leads, a positive lead and a negative lead. And I'm in the room light right here. And I have a voltmeter connected to them. And I find right now I'm getting about 0.69 volts out of the solar cell. If I cover it, the voltage goes way down. Now the voltage goes way up. But what's happening in this voltmeter is it's measuring the voltage of a solar cell. And the solar cell also has the equivalent of a man-made atom in it. There's the silicon in there. That silicon has two energy levels. And when a photon of light comes in from the sun, the photon gives energy to the electron and raises it up to the higher energy level. And then it drops down again. The energy of the electron drops down again, but it gives out electrical energy. It can spin a motor, it can light a light, it can create voltage and electric current. So in the light-emitting diode, we put electrical energy in, we got light out. In the solar cell, it's very similar, if reversed. We put light energy in, and we get electrical power out. And these things are going to work to help save the world from its energy dependence. Light-emitting diodes, as we find out when we did the grease spot photometer, if you compare a light-emitting diode bulb to an incandescent bulb, it was much more efficient. You got more light for the same amount of energy. And I noticed that some of the students out there commented that the grease spot photometer activity helped them to understand the difference between the wattage of a light bulb and the light that came out. By switching to light-emitting diodes, we can save energy, use less energy, burn less fossil fuel, and save the Earth from global warming a little bit. Also, with the expansion in the use of solar cells harvest the energy of the sun to power things. They do not burn fossil fuels. And so by combining the energy generation, the power creation from a solar cell with the efficient lighting from light-emitting diodes, we can really reduce our dependence on energy. So I think with this I'm going to wrap up the hangout and have Eric and Zeke say a last word. And I'll come over here to the table. Come around. There we go. And see a little bit more that way. Okay, there you go. Want to come in?
Yeah, and actually, can I mention? Yeah, I want to mention Gene Chang. Gene, can you come over here real quick? She's not going to go. Anyways, one of our heroes to help get everything up online is Gene Chang. She's not going to be here visually, but I just want to big shout out to Gene Chang for getting everything up and running for this course. And actually, you might be able to see Jean on some of the snacks. She's actually on some snacks with her family on it. I want to say I had a great time. We loved your questions. Yeah. And yeah, it was great interacting with people from faraway lands, even in California and close by too. Right. We had people to stay on the office interacting with us too. It's all great. And we had some of you visited the exploratorium during the course of the class. I was very impressed. Said hello. Yeah. So thanks for exploring light with us, and continue posting your questions, and we will try to answer them over the next week as quickly as we can. If you have questions on your assignment, write them into us. Great.
Thank you very much.
Thank you very much. Thanks. Have a great rest of your life.
Come to the exploratorium. Come to the online.
Yeah, don't do it just virtually. Be here. See ya. Bye.
Bye-bye.